Okay, so let's get to lipid peroxidation, really where we were going with all of this anyway. So we talked about our free radicals. So we went right back to the valence electron story. We said the outside shell wants to have 8 electrons in it. If it doesn't have the 8 electrons, it's looking for them. It's on the attack. It's looking for those electrons, looking for a place it can get them. Oxygen only has 6 electrons in that outside shell, so it wants 2 more. We have unpaired electrons in the outer shell. We're looking for more. We want to fill and complete that shell. We talked about our reactive oxygen species. We said if we take oxygen and start adding electrons to it, unless we go and add all 4 and get to water, we're going to stop along the way with a molecule that wants more electrons. And those are our reactive oxygen species. So those reactive oxygen species hanging out in the middle are the molecules that are going to drive our lipid peroxidation. So we talked about oxidation and reduction. Oxidation is losing an electron, reduction is gaining an electron. So we're going to be oxidizing a lipid. So peroxidation is still losing an electron, but the intermediate being generated is that peroxyl radical that we were talking about. So when we're breaking down lipids by oxidation, we call it peroxidation because we're making that peroxyl radical in the middle. So we're speaking very generally, saying we're breaking down lipids. We're breaking down particular lipids, and because of the structure, even though we said we're not drawing structures, naming, drawing, and that whole deal, we're not ignoring structure. The function follows the structure, as corny as it sounds to say that. So the particular lipids that are prone to peroxidation are our polyunsaturated fatty acids, PUFAs. So the poly part is what makes the particular part of this molecule susceptible to the peroxidation. They're prone to the peroxidation, and it's not really that they want to get peroxidated. The molecule that's driving it wants the electron for stability. This is always about trying to get stable, get other electrons. So the molecule that wants the other electron is a free radical. And we were just talking about free radicals. That outside shell is not full. They want it full. They're just always in attack mode. So it's our hydroxyl radical that's causing the problem. That's the attacker. So remember we had that chain of reactions. We were going ultimately to water, and we had the hydroxyl radical along the way. There was like one step back, wanting that 1 more electron to get to water. It wants that 1 more electron to get stable and get where it needs to be. So the lipid is the molecule that it's going after to get that 1 more electron from. So let's look at the structure of the lipid and why in particular is it a good, I guess, good victim to go looking for that 1 electron from. So let's look at the structure of our polyunsaturated fatty acid. So poly is more than 1 double bond, and of course unsaturated means we have the double bonds in there. So we've got our chain. However long our chain is, we'll just call it R. And like I said, whatever number of carbons, whatever length, let's just zero in on the middle of it or part of it. So we've got a carbon, carbon. Let's put our double bond there. And so on to our carboxylic acid. So we got our hydrogens and so on. So Remember what we said about double bonds? We had rules. They have to be no more than, no less than 3 carbons apart. So because they can be no more than, no less than 3 carbons apart, we've got a carbon in the middle that doesn't touch any double bonds. And you can put your hydrogens on if you want to make it more complete. So we've got that carbon in the middle that doesn't touch either double bond. That's called a methylene bridge. And it's because of this no more than, no less than 3 carbon apart thing for the double bond. So this is the carbon in between the 2 double bonds. It turns out that hydrogens are very reactive. So hydrogens are very reactive. So this is kind of an unstable-ish part of the molecule, if that makes sense. So what that allows that to happen is we've got this hydroxyl radical hanging out. It's in attack mode because it just is. We've got unstable hydrogens. There we go. It's attack time. So it attacks, and what it wants to do is make water. So if it can just get that other electron, it can make water, and mission accomplished for it. But it's what it does to the lipid that is really the damaging part. So the hydroxyl is now stable as water, but the lipid's not stable. The lipid just lost this hydrogen, so it just became a free radical. So that's the peroxyl radical that we were talking about. So it's the chain of events that goes through that can actually be damaging to our tissues. So like so many things we've talked about, we have, we initiate it, we do whatever we're going to do, and then we terminate it. We have an initiation, propagation, termination story in this. So initiate, do whatever we're doing, which happens to be propagation, the chain reaction kind of thing, and then stop, terminate, shut down the whole thing. So we're going to go through the steps, the mechanism, and the first part is that initiation. So I'm never sure drawing this, whether to draw the whole lipid part of it and focus in, or what to do. So I don't know, we'll figure it out. So initiation is where the free radical attacks the lipid, kind of what we just did, and it turns a stable lipid molecule, or what was a stable lipid molecule, into a free radical now. So one free radical got stabilized and made another free radical. So we'll draw the lipid the way we did a minute ago. I'm just going to put the H's, the hydrogens, right in. And if you prefer to draw the hydrogens in the molecule like this, do it. If you want to draw them sticking out, which is probably better for this, go ahead and do that. Whatever makes sense to you. I guess that just made that bond. Oops, really messing this up. Okay, and that's just a plain old single bond there. So this is our methylene bridge. And this is the vulnerable part of the molecule that the hydroxyl radical is going to attack. So like we said, these hydrogens are reactive. So what it's going to do, we have that hydroxyl radical. We can draw it this way. And what it's going to do is it's going to pull this hydrogen off. It wants another hydrogen. So here it is. and it makes water. So it's stabilized, it's fine, it's all good. But we just made water plus a lipid radical. So this now is going to become a lipid radical. So what that looks like, now we got that unpaired electron. And then the rest of the molecule to our carboxylic acid. So now, here we are with another unpaired electron. That's what we had a second ago. That's what we have now. Rather than the unpaired electron being on the hydroxyl, now it's on the lipid. So let's move that over to another slide. And we're just going to draw the same thing, the same hydroxyl radical. I'm sorry, peroxyl radical. And so on. So now we've got a peroxyl radical. We've got an unpaired electron. So we've got an unpaired electron. Unpaired electrons go in attack mode. They want to be paired. They're looking for another electron. So this is our lipid radical, also known as, AKA, our peroxyl radical. So now our next step is propagation. So this is where we kind of do the same thing over type of thing. So we've got that lipid free radical that we have drawn above, and we're going to add an oxygen to it. So what that's going to do now, the oxygen's going to attack at the methylene bridge. This is going to make our peroxyl radical. So our lipid radical now will have the oxygen on it. Still an unpaired electron. So this middle part is this middle part. We added that oxygen to it. So now this is our lipid peroxyl from here, well, the whole thing, but that's where the name comes from, peroxyl radical. The oxygen was added to it. So now that's going to go and react with another unsaturated fatty acid. So this is where it gets a little dicey trying to draw it, but we'll do what we can. So I'm going to take another unsaturated fatty acid, whatever it is. So what's going to happen now is we're going to get a lipid peroxide out of it. Remember we said these hydrogens, this probably needs another color. These hydrogens aren't stable. So what we're going to do is this hydrogen will jump over here, leaving now this part short, short an electron. So what it in effect did is turn this molecule that had its two hydrogens into this one. So it'll go and find another oxygen, make this, find another fatty acid, steal a hydrogen, back up here, find an oxygen, make this, steal a hydrogen off another one. It's kind of like, let's say, I don't know, let's say I get pickpocketed. So somebody took my wallet, and I thought, I don't like this. I'm going to go steal somebody else's wallet. So I steal somebody else's wallet. Then somebody else says, I don't like this. I'm without a wallet. I'm going to go steal someone else's. They don't like it. They steal someone else's. So that's what's going on here. This lipid, fatty acid, polyunsaturated fatty acid, got its hydrogen stolen. So it's going to get an oxygen, form this molecule, go steal somebody else's hydrogen. This lipid got its hydrogen stolen. Come up here, get an oxygen, become this, steal somebody else's. Back up, get an oxygen, steal somebody else's. So it's like, I got my wallet stolen, I steal somebody's, they steal somebody's, they steal somebody's. And that's our propagation. The cycle just continues like that. That's the damaging part of this whole thing. So we're going to do a termination step in a minute that shuts the whole thing down. But the problem is the damage is done by then. So what we're going to do in termination is I'm just going to draw an R. I love having colors. I'm just going to draw an R for this part of the molecule. So I'm going to draw this molecule as R and the 2 oxygens. So what R and 2 oxygens mean is this whole thing, the lipid peroxyl radical. I'm just making this part the R. So I'll just attach the 2 oxygens to that in the next slide. We'll do Palmer purple. Okay, so our next step and our last step is termination. So we said we've got an accumulation of the free radicals. So we've got an accumulation of these polyunsaturated fatty acids that have had the hydrogen stolen, the oxygen added. So we've got most of the structure and the oxygen hanging out there looking for an electron. So what we do if we have 2 of these is they can react together. So does it prevent damage? No, the damage is already done, but we do stop the process. So if I have 2 of these, they're going to react. So the proper way of drawing it gives me a peroxide. So I hook the 2 of them together basically. So they're done. They've got their electrons. They're happy. So that's my peroxide. And it gives me back an oxygen. So the 2 lipid radicals react, form the peroxide. They're done. We've terminated, form the oxygen. So it stops the chain. It stops the generation, the production of more free radicals. The big point in it, though, is that the damage to the tissues and everything have been done at that point. One of the very common questions that you get asked about what this damage is, or one of the answers with the common questions to what the damage is that of age spots. So if you notice with older people, sometimes you'll see these brown spots on the back of their hands. They're called age spots. Or a particular standardized test that you're going to take in about a year, we'll call them liver spots. And the liver spots result from lipid peroxidation. There's a pigment in particular that causes them, but age spots is what you're looking for. And it's from the cross-linked lipids, the products of lipid peroxidation.